Hey there, welcome to Pomodoro Joe for Saturday, November 11th, 2023. Today we're looking at LeetCode problem 2642. Design graph with shortest path calculator. This is a hard problem. All right, there is a directed weighted graph that consists of n nodes numbered from 0 to n minus 1. So that means we have some graph where it's directed. That means that you can only go from your from node to your to node. See, it has an arrow, but you can't necessarily go back. There might be a direction to go back, but you're not guaranteed that. So you have these directed edges. The edges of the graph are initially represented by the given array edges, where edges index I is equal to from sub I, to sub I, and an edge cost sub I, meaning that there is an edge from sub I to sub I with the cost of edges cost sub I. All right, so we're given this list of edges, and every entry in this edges list will have three values. It will have a from node, a to node, and a cost to traverse that edge. Implement the graph class. So it has three methods here. We have an initializer, which will initialize the n nodes. All right, we have an add edge, where we can add a new edge, and that will be a from, to, and an edge cost. And then we have a shortest path, which is node 1 to node 2. It returns the minimum cost of a path from node 1 to node 2. If no path exists, then we return -1. The cost of the path is the sum of the costs of all the edges in the path. Okay, so this is sort of a variation on some problems that we've done before where we're just calculating the cost of traversing some graph. All right, let's see here. We have a bunch of constraints, but I think this will be hopefully straightforward. So let's put 25 minutes on the Pomodoro timer and we will get started. Let's see. All right. So first, in our init, we're given this list of edges, which is a list of lists. Now, I'd really like to get this into a form that I can use a little bit easier, something where I can just take a node number and get back the list of edges connected to that node. So let's see, we can make a dictionary, or we can actually have another array here. So let's do that. First, let's store our n, just in case we need it. We might not. Let's see, self dot, I'll just call it connections. And then this will be a list where every value in the list, where the index represents the node value, and the value at that index will be it'll be a list of all of the connected nodes and their costs. So let's see, we'll have a list for every whatever in range of n. So what this will do is go from 0 to n and fill in that space in my connections list with an empty list. All right, now we need to fill in this empty list. So for every, let's see, we'll have node 1, node 2, and cost in our edges. All right, so for every value in our edges, we're going to get a node 1, a node 2, and a cost. So we're going to fill in our self connections here with that. So self.connections. For this node, node 1, we'll append. Let's see, we'll have, I guess I'll make this a tuple. We'll have node 2 and the cost. Okay. So now when we want to get all the connected nodes, we can pass in our current node, node 1, to our connections. We'll index into our connections array with our node 1. It will return a list of all of the connected nodes with their costs. Okay, I think that's all we need to do there. Now if we need to add a new edge, we'll just do the same thing here. We'll just add this new tuple to our connections. So let's see, I'll actually break it out like we did up here. N1, N2, and cost, that will be our edge. And we'll just add it to our connections. All right, now shortest path. This is going to be the hardest part of our problem. So for this one, we actually have to do our grid traversal here, or our graph traversal. We're going to start with our current node, and we need to try to reach our node 2. So let's do this. Let's start with some q. And that's going to just be our current node and the cost to get to this node. So that's node 1, and it costs 0 to get to this node. All right. Now, while we still have some nodes in our queue, we're going to have to process those nodes. So while our queue, let's grab this node out of the queue, and this is actually a node and its cost. So we'll do node cost is equal to q.pop. We'll just pop it index 0. And let's see, what's our end case here? Well, if this node is our node 2, then we're done. So if node is equal to node 2, then we're done, and we can return our cost. All right, now if we make it all the way to the end here, we won't have any cost. We haven't returned a cost. That means we must return -1. We didn't find a path. All right, now we're not done with this yet. I jumped ahead. So if we do find node 2, we found our path and this is our cost. We return the cost. Now if this is not node 2, well then we need to keep going. So we'll have to look at this node's connected nodes to try to find a path to node 2. So in that case, we'll say for every next node in the connected node list for this node, so that's our self.connections for our current node. And this is not just the next node, it's going to be the next node and the next cost, or maybe I'll call it additional cost. All right, so this is the next node, and it's going to cost a certain amount to get to that next node. So our total cost, so the next cost, or maybe I'll call it total cost, is going to equal our current cost plus this additional cost. All right, so we're going to be going from this current node, we're traversing this edge from this node to our next node. So the total cost will then be however much it cost to get to this node in the first place, plus how much it's going to cost us to go to this next node. All right, so now we have our total cost. And now we'll add this new next node entry into our queue here. So we need to go from this next node trying to find our node 2. So then our queue will append. Let's see, it's going to be this next node and the cost. Okay, so we're looking pretty good. We're going through our queue while we still have some nodes to process. We'll grab a node and its cost out of the queue. We'll check if we're at the end. If we made it to node 2, we're done, we can return our cost. If we're not at the end, then we look at all the nodes that were connected to this node, and we'll figure out how much it's going to cost to get to that node, and then we'll add that node and its cost to our queue to figure out if we can go from that node to our next node. So this is looking pretty good, but we might end up going in cycles. There are still some problems with this. There's nothing really stopping us from just going in circles and having this infinite loop in this while here. So we need to do something that will actually break out of this loop early if we end up in an infinite cycle. Now there are a couple different ways we can do that. One is to have a visited list, so we can make sure if we haven't visited this node before, then we can visit this node. Otherwise, we're not allowed to visit this node again. So we can do something like that. Actually, yeah, let's do that. Let's start out with that, a visited list. I'll make it a set, actually. So we'll have a visited set. Now, if this node is in visited, well, then we've already been to this node, which means that we don't want to keep going in circles. So we're going to have to just continue. We'll just continue with our processing. Let's not try to process this node again. All right, otherwise, we'll need to add this node to our visited because we're visiting this node now. So visited.add node. All right, so this is looking a lot better. So I think we are halfway there. All right, looks like I made one misstep here. So let's see. All right, when I append this next node, I don't append the current cost. I need to append the total cost. There we go. All right, let's try this. It's a long answer. Let's see. We're returning 8 here. So in this case, we're returning something that is too high. We're returning 8 when we should be returning 6. So what's happening here is we're just returning as soon as we find some cost. We're not continuing on to see if we can find a lower cost. So one thing we can do here is let's actually just keep a result out here, set it equal to infinite to start. And then when we find this cost, instead of just returning it, we'll check if it's better than our current result. So the result will equal cost if cost is less than our result. Else we'll keep our current result. And then at the end here, we'll return result instead of -1, but we have to check to see if our result is still infinite. So we'll return result if result is not infinite. Otherwise, we'll return -1. All right, try this. Still not right. I think what's going wrong here is we've visited this node already, but there is a better path to this node. So instead of just keeping track of if we visited or not, we have to keep track of how much it costs to visit this node and if we had a better solution or a better path to this node. So in that case, our visited set isn't quite going to work. Let's keep a cache. So now instead of just keeping whether or not we've visited the node, we'll keep track of how much it cost to visit this node and if we have a better solution or a better path to this node. So instead of calling this visited, I'll call it cache. And for this, I'll make, let's see, a list that starts initialized with infinite, and it's got to be of length n, so self.n. All right, so in that case, we don't need this result anymore because we'll be grabbing it out of the cache instead. So in this case, we'll return cache. All right, so now we've initialized our cache with infinite. It's of length n. So now in here, instead of checking if we've visited, we'll check first. If this cost is greater than our current cached cost, well then we'll just continue. We already have a better way to get to this node. Otherwise, we'll go on. And then in this case, we don't do result is equal to cost here. We'll actually check our cache. All right. Now, if our cost that we've calculated is better than our current cached version, then we'll store that in our cache instead. Let's see, everything else looks about the same. Let's try this. Okay, so this seems to work, but there might still be some optimizations we can do. Let's try this and see if we can pass all the tests. Time limit exceeded. All right, we only beat 1 out of 36 test cases. Wow. All right, let's jump back here. So what are some things that we can do to speed this up? So the first thing that comes to my mind is to replace this queue with something better. So one thing we're doing right now is we're just going through every single node, trying to find our shortest or least costly path from this node to node 2. Now, rather than go through and just explore all of our options, why don't we go through and explore just the lowest cost options first? So to do that, instead of storing a queue as a regular queue, we could store this as a heap. But that does mean we'll have to make a couple changes. So with our heap will keep things sorted and it will pop the minimum value out of our heap, but that means we have to swap these values around. We don't want our heap to be sorting on the node value. We want the heap to be sorting on the cost. So we're gonna have to do some rearranging. All right, let's see here. We can keep this the same. That's okay, but we'll have to switch this. So instead of node and then cost, we'll do cost and then node. All right. And then let's see, instead of doing a regular pop, we'll have to do a heap pop. So in that case, we'll have to change this to heap queue dot heap pop. We'll pass in the queue that we're popping from, and that should give us the lowest value. And instead of node and cost, this will be cost and then node. All right, let's swap this around. All right, we can still check this. If the cost is greater than the cache, we'll continue. All right, if we're at the end. Now in this case, well, we'll keep this for now. We might actually be able to return here. Now that we're doing this in the ordered of our heap, we might be able to just return at this point, but let's keep it for now. All right, then for next node and additional costs, so these are the same because we didn't change our connection, but when we push them back in, we have to swap this around. So our total cost comes first and then our node comes next. And we have to make this a heap push instead of a regular append. All right, this is getting more complicated here. So we'll do a heap push, heap queue dot heap push, and we pass in our queue, and then we pass in the value that we're pushing. All right, so this might give us a little bit of a boost. Let's try it, see if we're still working. Time limit exceeded. So this didn't work well enough. Okay, so then what can we do to make this even faster? Well, one thing we could do is instead of doing this like caching here, we could just return the cost. Because we're already going with the lowest cost route to begin with, this should give us the lowest cost when we reach this point. So that's one thing we can do. What's the other thing we can do? Well, in here, we could check our cost, this total cost, and check it against our current cost and make sure that we're not actually re-queuing something that's going to just cost us more in the long run. All right, so in this case, if we calculate the total cost, we only want to re-queue this node if this total cost is less than what we've already calculated for the cost here. So the cache for this next node. And then we'll re-queue it if this total cost is less than what we've already cached. Okay, and let's see, we need to update our cache. I think we do. I think we're missing the update here. All right, let's see if this gives us the boost that we need. All right, so that seems to do it. Okay, let's see if we can pass all the tests. Time limit exceeded, and we only beat 5 out of 36 test cases? Wow, that is not good at all. All right, what can we do to speed this up? Let's see. I think there's one thing, there's something that I think I missed here. So we initialize our cache with infinites, except, let's see, our cache for this node, node 1, should be 0. All right, let's see if that makes a difference. Still works. Let's submit this, see if we can pass all the tests now. Memory limit exceeded. Whoa, what? We'll use this test case. Why would my memory limit be exceeded? I'm not doing anything that crazy with my memory here. Well, we could try something else. Instead of doing this for every n, we could just do this for all of our connections. So self.length of our okay, we could try this. I don't think this is going to make that much difference, but it's worth a shot. Time limit exceeded. Let's see, what are we doing wrong? Down to 3 minutes. Let's see if we can do this. So we're going to grab the cost and our node out of our min queue here by doing a heap pop, or a min heap by doing a heap pop. We're going to check to see if this cost is greater than our current cached cost. If it is, then we'll just continue. Let's see. And you know what? I should be doing this check first. This is the very first thing we should be checking. Let's do this. Oh, I'm missing the most important thing. I did think about this. We need to update our cache. So our cache for this next node is going to equal this total cost. That's like the most important thing. How did I miss this? All right, try this one more time. Okay, let's see if we can pass with 1 minute to go. And we don't pass in time, but we do pass. All right, so that was the key. I was totally blanking on updating my cache. All right, and this actually does pretty well. We beat 88% for runtime, 43% for memory, so man. My apologies for totally missing the cache update. I don't know what I was thinking, but it's been a long week. All right, well, that's it for me. I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code. At least better than I do. Whew.